Hi, I'm Sean from the physics group. Our topic is to investigate the difference between Astyagak's pendulum under different circumstances. We were inspired by the problems in last year's IYPT, one of which suggested students investigating the phenomenon of a ball moving freely along a string that penetrates through it. And we found this very similar to a kind of toy called the Astyagaks. We thought it was interesting, so we decided to commence the experiment. We observed the pendulum and did some analyses. Then we changed the variation of the outer ball's initial horizontal component and the total length of the string. After that, we defined the transition period and discussed it. Finally, we simulated the pendulum. These are the equipment we had in the experiment. The data analysis software employed in our investigation is Checker, and the coding system is Python. We could see the two balls are falling freely at first. When the outer ball touches the bottom, it starts to do the circular motion around the inner ball, while the inner ball is doing a single pendulum-like motion. Here's what we found. First, let's take a look at the circular period of the outer ball. We count the time when the outer ball is right in the negative direction of the inner ball's x-axis, which means the outer ball is on the left side of the inner ball. As shown on the graph, the average of the period is getting bigger when the length of the pendulum is getting longer. In addition, the single pendulum period of the inner ball looks similar to this. We count the time when the inner ball is on the rightmost side of the system. In the next part, I will introduce the investigation of the transition period. In the beginning, our initial horizontal component is fixed at 25 centimeters. During the experiment, we found that if we increase the initial horizontal component, the experimental data will be in the state of chaos. And if the initial horizontal component exceeds a critical value, the test will make mistakes. This is why we want to investigate the transition period, which is the range of the initial horizontal component from chaos to faults. Then each of the chaos experiments is named transition. Next, I will introduce the parameter, the initial horizontal component, and the initial horizontal angle. The initial horizontal component is this length, and the initial horizontal angle is this included angle. Moreover, let's define what kind of experiment is called transition. Our definition of transition is that when the inner ball cannot make a complete pendulum movement, we call such an experiment a transition. In this picture are the results of our experiment. We can see that the initial horizontal component corresponding to the column of the transition period is what we call the range of transition period, and we call it transition for each test. It can also be seen that although different pendulum lengths correspond to different transitional periods, the initial horizontal angles are very close, mostly around 40 to 45 degrees. The last picture is a graph of time versus relative speed. First, the horizontal axis is time, and the vertical axis is relative speed. The relative speed of a successful experiment shows a steady and periodic decrease, while a transition experiment is chaotic, between 1.5 seconds and 2 seconds, and its cycle is relatively small. Next is the derivation of our theory. Since our Astyagak's pendulum belongs to a complex physical system, we cannot use simple mechanical analysis, like a simple pendulum, to analyze its trajectory equation. So we will introduce the Lagrangian equation to analyze our physical system. Lagrangian equation is the next formula, where L is the Lagrangian, T is the time, Qi is the generalized coordinate, Qi dot is the generalized speed. The algorithm of the Lagrangian equation is to partially differentiate the Lagrangian quantity concerning the generalized velocity, then differentiate the time, and lastly, subtract the Lagrangian quantity to make the partial differentiation of the generalized coordinate. The Lagrangian calculation is T minus V, where T is kinetic energy and V is potential energy. The next picture is a simplified diagram of our Astyagak's pendulum. You can see that the difference from the double pendulum is that the generalized coordinates are not only θ1, θ2, but also L1, L2, because the ball in the middle can slide freely on the string, so it is also a time-dependent variable function. So we can write the Lagrangian equation as follows, where Qi is equal to θ1, θ2, and L1. And there is no L2 because our total length is a fixed value, so we can write L2 as L minus L1, so that we can change our formula from 4 to 3, which greatly reduces our calculations. The last thing is to talk about the Lagrangian quantity, which is the kinetic energy of the first ball plus the kinetic energy of the second ball, subtracting the potential energy of the first ball and then subtracting the potential energy of the second ball. The last is the three formulas we get when we put Qi with three different parameters, and I'm going to explain the subsequent part of the program simulation. We simulated the double pendulum first. Although the equations you see in the last few pages are those of the Astyagak's pendulum, they are the extension of the double pendulum's equations. We took out the coefficient of the secondary derivative of theta and the constant term. Then we set up the coefficient to A, B, and C. The second equation followed suit, and we put that into the code. Then we could get the simulated animation, as you can see. Well, the problem with the Astyagak's pendulum is that we still couldn't find a relationship between the derivative of the length of the pendulum. So we are still trying to figure out the solutions to the simulation of the Astyagak's pendulum. In the end, I would like to conclude our presentation with a few points. First, the period of time gets bigger when the length of the pendulum gets longer, either the outer ball or the inner ball. Next, the Astyagak's pendulum is most stable when the outer ball is in the second, third, and fourth laps. Finally, though different lengths of the pendulum don't match the same range of the transition period, the range of the horizontal angles are very similar. We hope that in the future, we can successfully simulate the Astyagak's pendulum and compare the difference between the simulation and the experiment by changing the length of the pendulum. We also hope that we can add a vibration source to the experiment to find out the conditions where the pendulum can stay stable. Here's the list of references. And thanks for your listening.